Okay, this is the second lecture of week 7 after the midterm, and today is June 30th, 2022, and Dr. Stoilov, who's your thermodynamics professor, has asked me to swap this lecture with him because you have a midterm today. So I decided to record this and I will post it, and of course you're responsible for it. You can watch it at your own leisure. Now, what we want to do today is go through chapter 3, which is a discussion of a revolute joint. And once we do that, I'm going to show you how to create a trace once again, and how to create customized plots. So as far as the arm rotating about the base, it's just like a hinge of a door, essentially. So it's a revolute joint, and notice that remember that in a revolute joint, such as what you see here, hinge of a door, this bottom piece is fixed, and this hinges about that axis. So this has a 1 degree of freedom, and we're going to create this in the context of this particular problem. So we have a base that is fixed, that cylinder at the bottom, and you have an arm which is rotating about that common axis, and the length of the arm is given here, or this, let's say this piece is given here. And when I say 5 inches, it means from the center of rotation all the way to the tip is 5 inches. The shape of this is totally irrelevant for the purpose of this course. What is important is the distance from the center of rotation to where we want to calculate, for example, in the event that we want to calculate velocities and things like that. In other words, if I'm interested in the velocity and acceleration of this tip, I have to know actually this length. I'm assuming that it rotates at the angular velocity of 2 pi radians per second, which incidentally is 360 degrees per second. Okay? And the idea is that we want to, first of all, find the trace of this point. The trace of this point is obviously a circle where it's 5 inches, and find the velocity, x and y component of velocities, assuming that this arm lies in the xy plane, velocities of this tip. Now, this is the kind of thing that you have done in your elementary either dynamics or statics course, like that. So the position of x, y, x and y are given in that terms, and if you differentiate it, you get the velocity, x and y component of velocity, and if you differentiate it again, you get x and y component of this, the acceleration. Okay, and then you can plot these things as a function of time. For example, x dot and y dot, they're going to be sinusoidal or cosinusoidal. And of course, the acceleration is going to be also sinusoidal, and there we are. All right, so let's go ahead and do this problem. The first thing I'm going to do is I'm going to start with the product file. Please make sure you follow the instructions way at the beginning of this part of the course, because you don't want to get bogged down with improperly saving parts and products, and eventually things get messed up. Anyway, let's go back to assembly design. Okay, we are in assembly design right now, and I'm going to immediately save this product. So I'm going to say File, say Management, Save As. On my desktop, I create a folder, and this folder I'm going to call it Revolute Joint. Revolute Joint. Let's say June 30th. Okay, good. So product is going to go there. Then I'm going to insert my first piece. So insert, a new part in there, and that's going to be my base. I want to call this thing the base. Right-click Properties. I'll call it base. That is the part name, and the instance name also, I'll call it base. All right. let's go ahead and make it. Double click on the base so that we end up in part design. And in a convenient plane, on that horizontal plane, I will sketch a circle right there. The size of this base is totally irrelevant, but I will give it a dimension in case I want to have an idea how big these things are. So I'll make it radius 0.5. How about that? Radius 0.5. Exit. And then I'm going to pad it. The height of this is also totally irrelevant. So that's fine. So this is going to be my base. Let's go back to the product. Make sure you go to the product, okay? You don't do things in the base because this is a new part. Insert, new part, in there. Always say no. And I'm going to call it the arm. Right-click properties, arm and arm. There is the instance name. And there is a part number or part name. You say okay. And let's double click on the arm and try to make it. So on a convenient plane, on that XY plane, I will sketch something that resembles that arm that you saw. Actually, the shape of it is totally irrelevant. So here, I'm going to draw something like that, wrap it. Well, I'm going to wrap it around. So since I missed dragging it right there, and there we are. Okay. The only thing I want to know is the distance from this point to that tip, which I want it to be 5 inches. From here to here, I want 5 inches to match whatever is given in the problem description. Exit, and then pad it. Just make it so that it makes it nicer. So I'm going to make it 0.3. So there is the arm. Good. Let's go all the way to the top. Product. Click on the floppy so that the product and the two parts in it are going to be stored in that folder that I called Revolut Join and June 30th. Remember, on the test, you're going to have 3 problems. Each one of these problems should go in its own folder. Yeah. All right. So now we're going to start imposing the assembly constraints. So first of all, let's fix this. Let's fix this space. I'm going to click on it. Click on this anchor. This is the constraints toolbar. See that? The constraints toolbar in the assembly design. And I'm going to put the cursor on this part or in the tree, the base, and that's going to fix the base. Then I want to take this arm and stick it up there. So coincidence between the bottom of this, okay, and the top of that. And if I see that, if I say okay, and these don't quite become, flush, then you flip the arrows or change from same to opposite. Actually, we'll see. In fact, I believe that you have to flip the arrows. But anyway, let's say okay, see what happens. You see, it didn't. Actually, it really doesn't matter. It took the bottom. But yeah, you see that this top surface is flush with that. I wanted the bottom surface to be flush with that. And there are 2 ways we can fix it. Although as far as the mechanism is concerned, it makes absolutely no difference, but I like it to make it look good. To make it look good. So I'm going to double click on coincident, flip the arrows, one of them gets flipped, and then update, notice it shifts it up so that they become at the same level. I think. I'm not sure. They're so far apart that I can't really see. But we'll find out. I may have to do this thing again because I'm not sure whether I did it the way I wanted to know. But we'll find out. Coincidence the axis of this end and the axis of this base and update. So what it was originally was correct. Flip it. Click on it. Double click on this. Actually, let's say more so that we can see it. So you flip it. No. Hang in there. This one is the first one that I wanted to do. Sorry, not this. Double click on this. Flip the arrows. Say OK. And update. There. I like it better. Originally, what I did was correct. I just flipped it. It became wrong. Anyway, now it's okay. Now, notice that what we have created, two constraints. One of them is face-to-face, and then access-to-access. This is what a revolute joint is. A face-to-face, access-to-access constraint will lead into revolute joint. If you look at this joint, the face of this arm and the back face of this hinge, and the access to the two axes are coincident, and that leads into a revolute joint. Good. So let's go all the way to the top. We are already in the assembly design and save everything. Now we're going to go and switch to the mechanism design workbench. So you go to start. In your case, you're going to go to digital mockup, DMU kinematics. Go down here, DMU kinematics. Notice that what happens, the icon of DMU kinematic is something like that. I don't know how to describe it. I refer to it as the witch's hat. That's the only thing that I can, Halloween, the Halloween witch, it's got a black pointy hat. That's the only thing that reminds me of. Okay. Now we have created two constraints, assembly constraint, which can automatically create into, convert into a joint. So the way to do this, you go to this toolbar. First of all the joints are here. You can see that all the joints are here. Okay, but let me not use these things right now because these are, if you want to create these joints manually, I don't want to do that manually. So look at this other toolbar here, which says DMU kinematics, and there is one of them. There's one of them which looks like two gears meshed together. That reminds me of an assembly workbench. And then there is something here. This is a magic wand, which is magic wand. You click on it, which automatically creates some or all, depending on the situation, of constraint into joints. So you say new mechanism. By the way, notice that in the application, there's nothing here. As soon as you click on new mechanism, the name of it, you can give it anything you want, or call it mechanism. As soon as I did that, the application got filled with a plus sign. Say OK. And then you're going to say auto create. In other words, I created some assembly constraints, and if possible, I want them to automatically be converted to joints. Auto create, and let's see what happens. It says unresolved pairs, 0 out of 1. And then you go here, notice that the mechanism has been created. The name of it is mechanism number 1. The degree of freedom is 1. The joint is created, and it's a revolute joint. I could have done this thing automatically. And towards the end of the video, I will show you how to do this thing automatically. Now, if you expand it, you see that it's coming from those two constraints that I made. Plane to plane, access to access. Access to access, plane to plane. Degree of freedom is 1 because only the position of the arm is determined by only one thing, and that is the angle of rotation about here. Now, in order to animate and then put some physics into it, etc., this degree of freedom cannot be 1. Okay? What I need to do is you go here, you go to the revolute joint. I double click on this thing. You make this thing an angle-driven joint because it's a joint that requires a command. And that command is an angle. So you click on this, and notice that a blue arrow popped up here. It's kind of hard to see. You see the tip of the arrow is this way. That's why that guy is turning clockwise. If I don't want this thing, I can click. Let me zoom in for a second. You see that? If I click on this thing, click on this blue arrow, it goes the other way around. It goes counterclockwise. In this particular problem, we really don't care. So it doesn't matter clockwise or counterclockwise. Now, I want this thing to go from, for the animation purposes, I want to go from 0 to 360. Okay? So I can make this thing move in the direction that is selected, 0 to 360. That's for purpose of making a cartoon. There is no physics yet. We say okay. And notice that as soon as you do that, degree of freedom becomes 0 here, and it says mechanism can be simulated. And say okay. Now we can check our result. By the way, let's go ahead and save our just click on the floppy. It's going to save everything for you. Do not wait until the power goes out and you lose everything. Now here in the DMU kinematics, we already used this magic wand here. But there is this icon. See, there are two icons here. One of them says simulation with command that you will make it basically drag things, drag a bar, and this thing turns. This is where you put the physics into it. Simulation with laws. Right now, I want to show you the making of the cartoon. You click on this, there's only a single degree of freedom. That's why you get only one sliding bar. So if you move this thing, see that? And notice that of these two, I said immediate because I wanted to move immediately. You see this? As you drag it back and forth, this thing moves, okay? Let me put it back where it is. So we know it does what it's supposed to. Now, if I want to make a cartoon out of this without me dragging it, I uh, click on let me see now, right here, drag these things out. Let me see, I'm looking, oh, it's up here, right there, already up there. Look at the new generic animation. Over here on the left side, it says simulation. 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 You click on it, it says, okay, what do you want to, which one do you want to simulate? There's only a single mechanism here, which is mechanism number one. I want to select this and say, okay. So what happens, a similar dialog box opens up, okay? You drag this thing, this bar, you drag it, don't fool around with it just right now, just drag it all the way to the end. Once you reach the end, you say insert, okay? Insert. And then this will rewind it, we'll put it back where it was. Now change this number to anything but 1, because if you say 1, immediately it jumps to the end. But let's make it 0.1, anything but 1. And here's what we're going to do. Look, if I click on this triangle, play forward, this will move. Okay, rewind. If I wanted to play continuously, I'll change this arrow, one head arrow to two-headed arrows chasing each other and play. This basically goes in a loop. Now, it's basically a cartoon. There's no physics here. If you wanted to go forward and backward, you make the two arrows but away from each other. So it goes forward, backward, forward, backward. Okay, when you're done, just rewind this thing, rewind it, and you say, okay. Notice that the simulation has been created right there. Right there. There's no physics here. It's just a simulation. Now, I still want to work with these cartoons, no physics yet. So I go here, and there's something called compile simulation. Okay, if I want to find the trace of this tip, for example, or if I want to make a video clip so that I can put this thing in a PowerPoint presentation, etc., you have to compile it. First, you open this, where you create the simulation, you compile it. A dialog box opens up like this. It says, do you want to generate a replay or do you want to, for example, generate an animation file? Okay, so let's first do a replay. Do not use 1 here. Use anything but 1. So I'll use, I don't know, I can use 0.1, I'll use 0.4. Okay, so this is just creating a replay. And it's the first step in order to make sure that actually you can find the trace later on. All right, good. Look right here. So all I need to do now is double click on this, double click, and just play it. As simple as that. Okay, same thing. You have to just a continuous play. Good. So when you're done, I'm going to rewind, go back. Now that you created the replay, by the way, you can also create a video file. Let me also do that. So let's go here again, compile, another one. This time, I don't want to generate replay. I already have a replay here, animation file, and there's only one format that we have. That's fine. And file name, I'll put it in that folder, which was called Revenue Join June 30th. I'll call it my first video. This is just a cartoon, no physics here. Cartoon. Just give it time. Oh, don't use 1. Ooh. Don't use 1. Use anything but 1. you'll see that the video clip was generated in that folder. We're going to find out. Good. So let's see, where is that folder? I think it was here probably. Oh, no. So let's see now. Where was it here? June 30th. I'm going to join you June 30th. And there is my video clip. I can play on it. I can play it. And this can be, you can put it in your presentation, I don't know, document. Done. Done with this. Okay, let's go back to Katia. All right, now that we have created a replay, what we can do is there is an icon here. Notice that you have used already simulation, you have used compile, and there is an icon here that says trace. You click on it, this thing pops up and it says, okay, you have created the replay. You need to do that. Of course, you have compiled it. It says, what do you want to find the trace of? Well, I want to find the trace of this tip point, for example. Okay? And reference product, and this is going to be with respect to reference product that's fixed here. And this is the number of points that you're going to get on that circle. And notice that it's going to be created as a new part. You say, okay, just give it some time, and there we are, 26 points here. Now notice that it ended up in as a part. Now, if you go to file save management, by the way, file save management, you can see that this is the stuff that you already did, but this trace too was not saved, okay? So you say save as, in that folder, Revolut join June 30th, say my first trace, how about that? My first trace. Okay? Say okay? And say okay? And incidentally, if I close this, I don't have to close it, but I can minimize it. Here's my actual product or mechanism right there. If I want to bring the trace in here, you're going to say insert existing component, because you saved it, existing component in that product. And it says, well, where is it? So let's go find it. There is my first trace. See that? Say open, and you see that it's going to pop up in that window. Good. Now, in the event that you want to see your cartoon again, you double click on this, and you play it continuously. You see? Good. Close. I always want to rewind these things, but bad sign. Bad sign. This is going to crash. Right. Be prepared. Good thing I saved everything. Let me start Katia again. I'm going to open my product. Everything is going to be there because the good thing is that I saved everything. I don't know why I got that message. When you get that message, there's really nothing that you can do. It's going to crash, and unless you have saved it, you lost everything. Just be patient here. I started Katia. I think I did. Yeah. We're going to do the rest of the problem. Not to worry. Now we're going to put some physics into the problem. It's taking longer. There we are, longer than expected. You have not requested a configuration. That's okay. So we will request one. Say okay. Now you don't have these issues because you have a different version of. So it is the DMU kinematics right there, and I say okay, and I'm going to go open up that product. So file, it was that product, right? Yeah, there. Yep, it's in the application. The application. Everything that we did was saved right here. What was not saved is that when I did the replay, remember when I did the replay, I did not save that version. So it's very easy. Let's try it again. I'm not going to create a video clip though, so I'm going to go to let's create a simulation. But this is a good review. So once you created your mechanism and everything worked, like let me show you first of all, is everything working here? Let's go back here, manually drag this thing, make sure that it works. Yes, that works. Okay. So then I created a simulation for you. Let me drag this thing down here. This is the creation of simulation. You need to do that in order to compile it. So you drag this thing all the way, insert, choose anything but one, and then let's play it continuously. So yeah, good. So we stop it, rewind, and say okay. And simulation has been created, and if you want, you can create a replay, get the trace and everything, which I'm going to skip, by the way. I'm not going to do that. So now I want to put some physics into it. Now, when it comes to physics, it means formulas, right? Physics is basically math plus real world, okay? Math is right there. These somehow I want to tell uh, the problem that this arm is turning at a constant speed. So here's the situation. The first thing that you're going to do, you're going to click on this toolbar, which is, let me maximize this. There is a toolbar down here called knowledge. Usually this knowledge is down here at the bottom row, knowledge. And you see an f of x. As soon as you see an f of x, you know that, well, we're talking about formulas. You click on it, this thing opens up and it shows you all the stuff that we have done in this particular model. You know, the radius of the circle, the padded length, etc. But I'm not interested in those things. All I'm interested in is the mechanism. You click on the mechanism, there's only two things, time and the angle. See that? Remember, we make it angle driven, specify the angle, the 1 degree of freedom. As a function of time, we want to specify that. So the angle, this angle, as a function of time, is the angular speed times time. Omega times t. Remember, the the angular velocity of this arm is omega radians per second. And if you want the actual angle, you multiply it by time. So what I want to say is this angle, add a formula. Notice that here is the angle for that particular thing that we specified, equal to 360 DEG divided by 1 second. So 360 degrees in 1 second, which is one round per second, times time. Now, time variable is kind of weird. You can rename these things, but I don't want to rename it. Look in the second column here. If you click on this is the name of the time in this variable, in this problem. Either you can start typing this thing or put your cursor here, left double click, it puts it right up there. So now we have said that the angle is equal to omega times time. Omega in radians per second is 2 pi radians per second, which converts to 360 degrees per second. Remember, it was 2 pi radians per second, okay, which converts into 360 degrees per second. Okay, good. You say all right? Good. If there's any message, if you put extra characters there, you know, something does the syntax doesn't work, it'll give you an error message. Okay, so we say okay. Good. So now we have some physics. There is my law. There is physics here. Okay, there is physics here. Okay, so what we do is we're going to go to do see here sorry, right here, DMU kinematic. This was manually doing a simulation with laws. Simulation with laws. Simulation with laws. Formulas. You see there is a sign thingy, a graph there. Click on it. It says, okay, what's the total duration of the time that you want to simulate this thing? The default is 10. Let me change that thing to 2 seconds. That means the arm will turn twice. Good. So, we're going to play it. Once, twice, stops. You might say, wait a minute, this could be a cartoon. Well, the only way for me to figure out is to go and plot the x and y components of the velocity. Okay, so let's rewind this thing. We say, okay, to plot the x and y components of this point, velocities of this point, what I need to do is to create a sensor. There. If you put the cursor, this is one of the major toolbars in this DMU kinematic. If you put the cursor there, it looks like a ball rolling down a ramp. If you click on this, it says, okay, well, first of all, what do you want to call the sensor? I'll call it speed acceleration. Okay? And it says, what is the reference product? Well, the reference product is the base, okay? And what is the point? I want to plot the stuff about this point or that point, by the way, they're the same, okay? I mean, as far as velocity is concerned, they're the same. We say, okay. So we have created a speed and acceleration sensor. You can create several of these because you may want to plot different things. Now, here's what you're going to do. Once again, say simulation with loss. Here, simulation with loss. We just did it a minute ago. Except that we're going to say activate sensor. See that? Activate sensor. You click on it. It says, okay, what do you want to activate? Well, let's do a few things here. So first of all, I want to activate see, they're all nodes to begin with. I want to activate the angle. So as soon as you click on it, it turns into yes. Then I want to plot the x component, x linear speed, x component of the velocity of that point. So I click on it. And the y component, I click on it. And the acceleration. This, by the way, this is going to be, these are the x and y component. If I click on the linear speed here, instead of x, y, z, obviously z is 0, linear speed will just give you the magnitude of these two, square root of this square plus that squared, okay? But I don't want to. X and y component of the acceleration, these are all yes. And notice that at the very top, I also did the degree because I want to show you something later on. Okay, now, don't do anything foolish. Just leave this stuff here. Leave this stuff here. Don't close this. Move it out of the way. And play it. What's going to happen? This is going to go around twice because I asked for 2 seconds. This is once. And this is twice. And it's going to stop. So move this thing up and say graphics. Click on it. So I plotted 5 curves. Angle, x component of velocity, y component of velocity, x component of acceleration, y component of acceleration. By the way, if you can't see all these things, you just zoom out. Just the usual zoom out. Either here or from the zoom in, zoom out of the, and here, even here, I think you have to make it bigger. Maybe you have to drag these things so that, yeah, you can see the rest of it. Zoom out. Now, once you select any of these curves, the color on the vertical axis becomes the unit of that. Notice that this is the angle. Going twice means, as a function of time, it goes 720 degrees. Okay, and it increases. This yellow one says that the angle increases linearly as a function of time. No big deal. If you click on the x component of linear speed, it becomes this blue one, which is the sinusoid. Y component, green one, which is also sinusoid. Okay? And incidentally, the magnitudes are the same. If I notice that the magnitude of this green one is inch per second. So this is, remember the formula is R times omega. Okay? Omega is 2 pi. Okay? Omega is 2 pi multiplied by the radius, which is 5 inches. That 10 pi is roughly 30 something, 31. Okay, so it goes to 31. Even if you select on the blue one, oh, this is acceleration, sorry. The linear speed, y component linear speed, the red one is again 10 pi, you can see that. But if you go to the blue and green, this is going to be r omega squared from your dynamics class r omega squared, and your omega is 2 pi r omega squared, or is 5, you're going to get the maximum value that you see over here. Now, I want to show you something else. First of all, by the way, on the final exam, we're going to ask you to generate some graphs. And because once you close your account, CATIA, you log out of CATIA, this is all going to be lost. I'm going to ask you to print screen this, go to maybe, I don't know, whatever you got. I'm going to go to Paint. I'm going to say paste there, File, Save As, Desktop. It's going to go in that folder that you created, which was called, what was it called? I forgot. Hang in there. It was called, oh, Revolut Join, right here. I'm going to give it. So my 5 requested plots, because on the exam we're going to ask you to plot, to create a specific specific graph. So for example, a JPEG, I'm going to save it there. So, and when you submit your work, you better give us that by requested plot also. Okay, this one. This is going to go along with the product assembly and all parts making that assembly, including the trace if we ask for it. Okay, so all the product and all parts and this graph that you generated. Now let's go back here because I want to ask you to generate something else. When I close this, unfortunately, it's all going to be gone. So first of all, rewind it, and uh, when you rewind it, the history is still going to be there. If you click on the history tab, clear the history tab. Okay. What I want you to do is to plot x component of the velocity, linear speed, versus the y component of linear speed. This is where you go to option. Notice that I don't want versus time. I want x linear speed versus y linear speed. So you go to options. It's a customized plot that I want to generate, and it say add. It says, well, what do you want to plot against what? Well, I want, for example, x linear speed versus y linear speed. And guess what? This is going to be a circle, because go back to the formulas that you had there. If you take the x component of speed squared plus y component, actually you're going to get r omega. Omega is 2 pi. If you square them and add them up, you get r omega squared. R is constant, omega, so you're going to get a circle. We say, okay, we close this. Now we play it. Don't close this window. We need it. I'll just move it out of the way. 2 seconds. It's going to be a circle on top of a circle, because when 2 seconds, we go here and we say graphics. There we are. And print screen, if we ask for this plot, print screen, go to paint, paste. I mean, I pasted everything, but you could have just, selected that part of it. File, save as, save as, my desktop, Revolut Join, etc. Or use the JPEG, for example. There's already one here. My customized plot, my requested customized plot. If these things are missing and they have the wrong units, We're going to ask you what user units you're going to lose some marks. So in that folder, oh, not this one. Let's see now, I can close that. I can close this, I don't need it. And let me see for a second. There is a folder, my 5 requested customized block, and actually it was not 5 requested, it was just my requested customized block. Let me change the name of this thing. My requested. We're going to ask you to do these on the final exam. Okay? So where are we? Right there. And we're done. So I always rewind. I close this, and I close that, and I save everything. Okay, in the next 5 minutes, I'm going to show you how to do the same problem without actually using the magic wand. So I'm going to close this. That's gone. Let me go to assembly design. This time I'm not going to worry about the units and physics, and because we already know. So insert new part in there. This is going to be my base, right? I'm going to be clumsy. Just leave it as part 1. That is clumsy. Let's go make it. Double click on part 1. Very clumsy. I don't like it. So, but I'm also clumsy when needed. But, okay, so let's see now. Here is the circle. Exit. Pad it. That's fine. Now we're going to go to product. I'm not going to save. Those are things that you have to do. Insert new part. Always say no. Let's go make it. Double click on part 2 so that you go into part design. On a convenient plane, on that XY plane, for example, I will sketch. Remember that arm? So it was something like that. I'm not going to worry about dimensions. Exit. Pad it by 0.3. Okay. Now, because you are not using the magic wand, you really don't have to put assembly constraints here. But I would like to fix something in space. I would like to fix this space. If I don't, then when I try to make the joint, it's going to say, "Hey, nothing is fixed. You wanna fix it there." So actually, you know what? Let me not do this. Let me not do this. But I'm just telling you that if I fix this thing, anchor this, I will not get this message that you see later on. It's all right. So you go to start, digital markup, DMU kinematics. Okay. Now notice that when I try to use the magic wand here, see that? When I try to do this, it's going to tell me that there are no constraints. You see, there are no constraints, no problem. You say okay. So what I'm going to do is I'm going to create the joints first of all manually. I'm going to anchor this guy. There is the anchor. I'm going to click on anchor. And I'm going to select. As soon as I try to select this, says, hey, wait a minute, there is no mechanism. So let's say new mechanism, mechanism number 1, and now I select this. So it anchored it. Now I want to create a revolute joint between this piece and this piece. So revolute joints, all the joints are here. And the revolute joint is the very first one, revolute joint. You click on it. It says to do a revolute joint, you need two planes and 2 axes. So let's do it in order. Line 1, this is going to be axis right there. And for the next one, you have to, I think you have to do it, yeah, you have to do it in that order. Next one is plane, oh, line 2. Okay, it's asking for line 2 now. I was trying to select the plane, but it's asking for line 2 right there. This axis, so it's the order like that, axis to axis, and then plane to plane. For the plane, I'm going to use this, and for the second plane, I can use the top or the bottom, but then you may have to flip arrows in case you don't want to. Now notice that the angle-driven icon is here, but let me not use that right now. I'll just leave it the way it is. You say okay. Notice that it did the assembly constraint automatically. It did it for me. Now, if I want to make this thing angle-driven, okay, first of all, oh yeah, right here. See, automatically the constraints were created for me, but mechanism has been created, degree of freedom is one, the joint is revolution, and if I double click on it, I can make it angle driven, which I could have done it earlier, but I decided not to. There we are. There's the blue arrow that you saw, and the rest of the problem is exactly the same. You want to do that manually, right there. This is a good review. So there it is. This is manually. Once you do that, you're going to create a simulation in case you want to make a cartoon, you want a video clip, you want to make a trace, you have to create this. Drag this thing all the way to the end, insert, rewind, anything but one, and play continuously. There we are. Good. Continuously. So let's stop this thing, rewind, and OK. Let me remind you how you create compile things. Let me move this thing out of the way, open this up. The second one says compile. You have to create a replay if you're going to do the trace and things like that. Replay and yeah, anything but one. And patiently say OK. It's going to create a replay right there. And to create the trace, you need this replay. It says element to trace out is this vertex, 26 point. You can make it probably more. Yeah, I can make it more. Let me actually make it 60 and say OK. It's going to do it for me right there. I don't know whether it took 60 or not. Maybe I didn't. Maybe I didn't change it to 60. Still 26. Yeah, I could have made it bigger. Okay, so save this thing, file, save management. The trace is not saved. Save it in that folder. Now, I didn't save any of this stuff, but let's say hypothetically that we wanted to do this. So the whole thing, save it. So product, save as, one level up. My second run, my, my second run, manual joint. Everything goes in there. And you say okay. You say okay. And you say okay. Now, yeah, let me, yeah. So let me say okay. We're going to check it. See if the trace is also there. So my second run right there. See, the trace didn't go there. I should have selected it, or probably select save directory or propagate directory. Notice that it took these, put it there, but not the trace. Be careful. Okay. Now let's do something else before we quit here, and we go back there. And now we're going to say File, Save Management. This is the trace. Save as in that same folder that I missed. We can call it trace 2, whatever. Save there, and we say OK. Now it's going to be in that folder. Oh, oh, I must have screwed up. Oh, this went to the wrong place. Okay, so let's go ahead and do that again. Go back here. File, save management. This was the one, save as, in the right folder. Oh, this is not even the wrong one. So one level up, my second run, trace 1. Okay. So it should be there. There we are. Do not miss this. So easy to miss these things. Now, the rest of putting the physics into it, etc., you can go back and watch the rest of the first part of the video. Now, a word of advice. These lectures were also presented in more or less similar fashion. The content was the same, but it was done last year. So if you're finding some flaws in this video recording, I suggest you go to last year's presentations and watch the video that was on last year. Maybe I said a few things there that is more amenable to a palate. I don't know. Maybe today I had, I don't know, too much coffee and I went too fast or too slow, etc. But in all likelihood, that was not the case last year. Good luck. The next four videos for the missed lectures and the two tutorials labs that are the GAs are going to be running are going to be recorded the same way and posted on YouTube for your inspection. Now, just one more time, this is a fast-paced course. We have noticed that people who did not stay with me during the first 6 weeks of the course and thought that they were going to catch up in the last week or so, it didn't work out that well. It's going to be tougher this time because there is, you know, more stuff, or not harder, and not even more stuff, but you have to stay on top of things. You cannot do this thing, leave a gap, and then thinking that you can catch up later. Good luck.